The subspace V of R3 contains the vectors 0, 2, minus 1 and root 3, 0, 0, but does not contain the vectors 0, minus 1, minus a half. Find the dimension of and a basis for V. Okay, so let's be sure I know what the question's asking me to do. It says I've got a subspace V of R3. Now I actually know what all the subspaces of R3 look like. They are the origin itself, a line through the origin, a plane through the origin, or the whole of R3. So it shouldn't be too hard to actually figure out what V is. Now I've been asked to find the dimension of V and a basis for V. Well, normally the dimension is the number of vectors in a basis. So normally I have to find a basis to find the dimension, but it's telling me I should find the dimension first. I suppose that's not that bad because I know that a line has dimension 1 and a plane has dimension 2 and all of R3 has dimension 3. So if I can figure out which one of those it is, I can actually find the dimension without knowing a basis already. And then once I've got that, then hopefully I can figure out a basis. I need to know what a basis is. It's a set of vectors in V that spans V and is linearly independent. And it will have to have the right number of vectors as well, if I know the dimension already. Hopefully that'll be enough to actually do it. Let's see what I can do. What I know about V. It's got these two vectors in it. And they're not the zero vector, so it can't be just the zero vector. These two vectors are linearly independent because they're not multiples of each other. See, I can't produce a root 3 in this spot by doing multiples of a 0 in this spot, so they must be linearly independent. So I can't get two linearly independent vectors in a line because all the vectors on a line are multiples of each other. So it's got to be at least a plane. Okay, so I should write something like that down. So V contains two linearly independent vectors. So, well, that means it's at least a plane or possibly all of R3. So since it's got two linearly independent vectors, the dimension must be at least 2. So the dimension of V is greater than or equal to 2. I wonder if I can do that in Rn. Yeah, I reckon I can because I know that the size of a basis has to be the smallest number of linearly independent vectors I can get. So if I can get a certain number of linearly independent vectors, then the basis must be at least that big. So the dimension has to be at least that big. Okay, so this doesn't actually require me to know that I'm in R3 to know this fact. So what next? What are the other options for the dimension? I'm in R3, so I can only go up to dimension 3. Can I get all 3 dimensions of R3? Well, no, I can't because that would mean that V was all of R3 and it doesn't have this vector in it. So the dimension of V must actually be equal to 2 because it can't be 3. So let me write that down. V does not contain all vectors in R3. So the dimension of V is not equal to 3. Therefore, the dimension of V is equal to 2. So we've found the dimension. That's good. So that means it must be a plane. Well, I know that a plane is spanned by two linearly independent vectors. And I have two linearly independent vectors in V, so they must be the basis. I think it's as easy as that. They're definitely linearly independent. They definitely span a plane, and V is a plane, so they span V. So they're linearly independent and they span V, so yes, they must be a basis. Okay, so the vectors 0, 2, minus 1 and root 3, 0, 0 are linearly independent and span a two-dimensional subspace. just to be formal about it instead of saying plane. But V is a two-dimensional subspace. So they span V. So therefore, since they're linearly independent and they span V, they're a basis for V. Therefore, our basis for V is 0, 2, minus 1 and root 3, 0, 0. The end.